Electromagnetic induction. This problem is very similar of an end of chapter problem in a physics textbook. We've got a loop of wire off to the side of a long current carrying wire. And if that loop of wire is just sitting there and that current is not changing in the long wire, then there's not going to be much happening in the way of generated voltage or generated current in that loop of wire. Right? Something has to be changing. So there are a number of ways to make it change. We can move this loop of wire, pull it further away or push it closer to the long current carrying wire. In fact, you can go ahead and try that. Your textbook probably has a problem just like that in the back of it. And then the magnetic flux would be changing through that little loop of wire, and we'd be generating a current. Or we can change the current in the long wire, which is what this problem is all about. So I1, the current in the long wire, is going to be changing, and we're trying to figure out what I2 is, the current in the loop of wire. Okay, so if we are getting a current in that loop of wire, there must be an EMF. There must be a voltage that's driving that current, and we can use Faraday's law to tell us what that voltage is. The change in flux with respect to time. And this minus sign, I'll tell you what I'm going to do. I'm just going to get rid of it right now and find the magnitude. That minus sign doesn't really help me much. You know what I do? I use this to find the magnitude, and then I use Lenz's law to determine the direction. We'll do that at the end. Okay, so I like to actually plug in here my equations, and I do this every time because students want to take little shortcuts, and they often take a misstep when they do that. So I write it out like this, and what students like to do right away when they see magnetic flux is just to write magnetic field B times the area A. And that is only true if your magnetic field is constant over the area. And in our case, the magnetic field is not constant over the area. The magnetic field from a long wire falls off as 1 over r as you move away from the wire, and so the magnetic field is different over different parts of this rectangular loop of wire. So we actually have to do this integral. So let's go ahead and set that up. The integral of B dot dA. So let's take a quick look here. The magnetic field from a long wire is going to form circular rings around that wire, and everywhere to the right it's going to be into the board. And everywhere to the left it's going to be out of the board. And I'm trying to indicate that as you move further and further away from the wire, the field gets weaker and weaker. That's why I'm spacing them a little further apart as these X's and dots as I move away from the wire. But so our magnetic field at this wire is into the page. So it's perpendicular to the page, and so what we end up with is the integral of B dA, and either a cosine of 0 degrees or a cosine of 180. But all I care about is the magnitude right now. So this is just the integral of B dA, because my magnetic field is perpendicular to the loop of wire, the plane of the loop of wire. And what is the magnetic field? This is the magnetic field, let's go back up here, caused by this long current carrying wire. And so the magnetic field from a long current carrying wire is mu naught I over 2 pi r. And I'll just leave dA the way it is for now. So we're still working through this. And now I have to jump back up here one more time, and we have to figure out what our area element is that we can integrate over. So I'm going to pick a small rectangular section here, and that's my dA. And so this long side is just L, and the short side is, I need to make some room here. The short side is dr, because we're moving away from this, we're r distance, let me just draw that in here. We're r away from the wire, and so that distance is dr. And we're integrating from A to A plus W, right? Let's go back one more time. We're starting at A and going to A plus W over this whole, we're basically integrating over the area of this loop. Okay, so what do I have here? I get my constants out. Mu naught is a constant. I is not constant. It's a function of time, right? It changes in time. But we're not integrating over time here. We're integrating over a radius, right? Over r, distance away from the wire. And so I is not a function of r, so we can pull it out of this integral. L is a constant. 2 pi comes out, and that leaves me with the integral of dr over r from A to A plus W. And that gives me a natural log of r. Evaluated from A to A plus W. And the natural log of A plus W minus the natural log of A is the natural log of A plus W divided by A. Okay, so now I have the flux, and now I have to take the time derivative. I have to go back up. I'm trying to find my induced EMF. So now I have to take the time derivative of this. I'm just going to rewrite this here. EMF is the time derivative of the magnetic flux, and that was my magnetic flux. So I can put that in here. The mu naught is not a function of time. L is not a function of time. 2 pi is not a function of time. A's and W's are not functions of time. They're constant. So the only thing is the current that's a function of time. So I have to take the derivative of the current with respect to time. Everything else comes out in front of my derivative. And the derivative of I with respect to time is, what is it, 4t, because it's I is 2t squared plus 8. So we take the derivative, we get 4t. And then we can plug in the numbers here. We're looking for the induced EMF at the time when t is equal to 2 seconds. And we know our mu is 4 pi times 10 to the minus 7th. L is 3 meters. 2 pi. We've got the natural log of 3 halves. And we've got 4 times 2 is 8. We plug in t equals 2 seconds. And we get 1.95 times 10 to the minus 6 volts. And now we can look at our small loop. So that's the EMF generated in the small loop, the voltage generated in the small loop. And if we know the resistance of the small loop, we can calculate the current in the small loops, because V equals IR. And so I got a current of 3.89 times 10 to the minus 5 amps. And let's take a look at the direction now. I'm going to go back up to my drawing. The magnetic field through that loop of wire is directed into the page. We've already talked about that. And at t equals 2 seconds, it's increasing, right? Because I is a function of time, 2t squared plus 8. So as t increases, the current increases. And at t equals 2 seconds, the current is a little bit bigger than it was at t equals 1.9 seconds. And at t equals 2.1 seconds, it's even going to be bigger. It's increasing right now, which means our magnetic field is increasing because the magnetic field is proportional to I. So we've got magnetic field into the page and increasing. So a current is going to get set up to oppose that, to try to reduce that magnetic field. And so it's going to go in the counterclockwise direction. So its magnetic field comes out of the page and tries to reduce that increasing field that caused from I1. It's a little tricky as I try to talk through it without being able to make hand gestures and things. So think about it a little bit, but it always opposes the change. The induced current always forms in such a way so its magnetic field opposes the change in the magnetic field that created it. So if the magnetic field that created it was decreasing, it's going to try to add to it, to strengthen it, to get it back to where it was. In this case, the field was increasing, so it's going to try to subtract from it, to take away from it, to get it back to where it was.